Hello everyone, this is Poornima Deepthi working as an assistant professor in the Department of Electronics and Communication Engineering at MLR Institute of Technology. So today's video is about assembler directives of 8086 microprocessor. This video is a part of series microprocessors and microcontrollers. So coming to the overview of today's presentation. So, what are the assembler directives? Why we are using assembler directives to write your programs in 8086 microprocessor? What are the key assembler directives present in 8086? And segment directives, data definition directives, control directives, what are the pointer directives, linking directives, and equate directives present in 8086 microprocessor. Coming to the introduction of assembler directives, what are assembler directives? Before going to assembler directives, what is assembler? Why we are using assembler? So normally assembly language is a less complex program which is user friendly program. To write the programs it is easy to understand, but here while we are writing the instructions are in the format of mnemonics rather than in machine codes, zeros and ones. But the machines which can understand, the processor can understand only binary language by using zeros and ones. So to understand the binary language, assembler is used to convert the logical assembly, whatever the mnemonics we are writing, to the understandable zeros and ones to the processor. So microprocessors and microcontrollers understand only machine language. To translate assembly language into machine language, we are using assembler. So here coming to the assembler directives. So assembler directives are the keywords which will be understandable by the processor easily. So to reduce the complexity of writing the program, some keywords have been given for the assembler, to which makes the programmer to write easy programs. So programming easily. So coming to the directives, there are segment directives which is used to define the segments. Here the main memory is divided into code segment, extra segment, data segment, and stack segment. So to specify these segments, we've been using segment directives. And end. So if we start the segment, we need to end that particular segment. So to end that particular segment, we've been using end segment. And to stop the procedure, we've been writing, or the subprograms we've been using in the processor. So to end that particular procedure, we've been using end P. So coming to the data definitions, we need to allocate some memory locations for particular data. So this DB is used to define byte, define word, define double word. DUP means duplicate memory starting from the 0th location. So coming to the control directives, to end the program, to assume CS, like we will write assume CS. So we've been matching the register to that particular segment. So here assume is used for that. And origin, to start which address location the program need to store. Even, it will fetch only even address locations. So coming to the pointer directives, so how we will using this pointer for word or byte, like that. Far or near means we will be using the segment within the segment or the other segment in that particular segment. So scope and linking directives means public and external. We will defining the data in one particular segment, that data can be, that variable can be used for in another segment. So how to use that particular segment variable reserved in that particular segment in another segment. So coming to the equate, we will be assigning one value to that particular label which we are equating. So in first segment, so it will define the logical block. As I already told you that 8086 memory is divided into 16 segments. Out of this 16 segment, at a time we will use only 4 segments, and out of these 4 segments we are having code segment, data segment, stack segment, and extra segment. This data and stack extra segment are used for to design the data, and code segment is used to write the particular code, and stack segment is used to hold this intermediate or status flag registers into the stack segment. So coming to the example of this particular segment, here I was defining one data within this data segment. So I was telling that the data segment is starting here and this particular data segment ends here. End is end segment. Which segment we will be starting, that segment will end here. Between that we need to, this is the data segment, so I was assigning some data in this particular segment. Here var1 is the label, so here db, define byte, so 10 will be stored. For 10, byte location will be reserved. So for 10 number, the location reserved is byte. 1 byte memory will be reserved. That byte memory, that location is specified with the var1. So according to this particular program. So it will create the data segment. If we want code segment, the same we can use code segment and we will write code here, and last we need to code ends. End S represent end of the segment. So end of the segment. This is about the segment directives. Coming to the another segment directives is the proc. Proc means it is the procedure or subprogram which will be used by the main program. Set of instructions are said to be in the proc procedure. So end. So if I want to write some instructions in this procedure, move ax comma bx, and here I was mentioning one procedure name. Here let us take this example. Here the procedure is label, name of that procedure is myproc. So this is the procedure. So under this procedure until end procedure, the lines between these procedure will be under the subprogram. So if we want to use this subprogram in particular main program, we can call this procedure by using the title of that procedure. Until end P finds the lines between these two, the starting of the proc procedure and the end procedure, the lines between these are considered as the subprogram. So coming to the next data defined words. So if we are defining the memory located for that particular number, here allocates 1 byte of memory. Out of memory, 1 byte of memory will be allocated for 10. So 10 under the name of var1. So if we are defining DW, defined word, in this particular directive, it will allocate 2 bytes of memory. So in this particular memory location, these 2 bytes will be allocated to store 1, 2, 3, 4. As I already told in the previous videos, the lower byte will be stored in the first memory location and the higher byte will be stored followed by this memory location. So these 2 bytes of memory will be reserved for 1, 2, 3, 4 number under the name of var2 according to this particular instruction. Next DUP. Here like DD word will be there, DQ word, define quadruple words, DT words, define 10 bytes. Those are the other assembler directives in the same data definition directives. DQ means it will reserve quadruple bytes and DT means it will reserve 10 bytes of data for 10 bytes of memory to store that data. And here DUP, duplicate values, it allocates multiple bytes with the same values. So if after performing some operation we didn't know how much of memory is needed to store that particular result, so in that particular instruction, in that particular situation, we can use this duplicate memory. So DUP, duplicate memory, it will allocate, if mentioning on the I need to have 5 duplicate memories, so it will start with the initialized with the value 0. So 5 memories will be reserved for this location with values 0. This under the name of ARR. Here it doesn't mention. This is the label which we are giving to represent these 5 duplicate memories, ARR. Next, coming to the next one, control directives. This directives controls the execution of the program. Here end means it represents that the program ends here. End start. To execute the main program, while writing code segment, we will be using start directive. So here we are mentioning that we've been starting the execution of the program. These are the code lines. After start, we need to write the main code lines. Before code segment, we can initialize data segment, as I already told you in the previous slide, that how to initialize the data segment. We can assign variables, we can assign values to that particular labels in that data segment. And this particular code segment, we need to start the code segment with the assembler directive start. So officially we are starting the code to implement in this code segment. So until when this start will stop, if we mention end start at the last of the code segment, then up to this, these are the main code lines to execute for the 8086 microprocessor. So coming to the assume, this particular directive links segment registers to segments. So as I already told you, we have 4 segments: code segment, data segment, extra segment, and stack segment. But the registers which hold the starting address of these particular segments are different, because the code segment starting value will be stored in the code segment register, data segment register, extra segment register, stack segment register. So these particular registers will be linked to that particular segments. So to link the segments register to segments, we've been using assume. So if we want to use only 2 segments in the program, you can assume CS code or DS data. If further instructions, like if we are performing string manipulation programs or string programming on strings, then we can include ES, extra segment. If we want to declare status stack segment, yes, you can use SS, stack segment. Like this, we can link segment registers to that particular segment. So I want to start the program, writing of the program. I need to store my program at the location, so some perfect location, like I want to start my program with 2000. So to start the program with that particular address location, we can use ORG, origin. It will start from that particular address location. So coming to the even assembler directive to use the only even address location. Suppose let us see one example. If this is the memory, so the address locations like 00, 01, 02, 03, 04. So out of these address locations, if we are using even, these odd locations will not store the data. So only even locations will fetch. Even locations only stores the data continuously. Like here I was defining word, so I was locating 1, 2, 3, 4. So in this particular memory location, this is the even address location, this is odd, even, odd, even. So whenever we are storing, generally 3, 4 will be located here and 1, 2 will be located here. But in this particular, we have mentioned even, so only even address locations will be allocated. Like 3, 4 will be stored in this particular even address location, and then 1, 2 will be. These odd locations will never save the data. Why we are using only even locations? While I was discussing the physical address memory of 8086, I have told that the total memory will be segmented like 2 different parts. One is even location and one is odd location. Because to fetch the data present in even location will be executed fast when compared to the data present in the odd locations. To avoid that delays, we can use this even assembler directive, so it can align the next data or instruction in the even address location. So execution of this particular instructions is little bit fast when compared to the data present in the odd memory locations. So coming to the next one, pointer directives. This specifies the type of that particular pointer. Here move AX comma word. Word is the pointer. So a word data will be loaded into the pointer BX register. So the value present in BX is the address. In that particular address location, 1 word, like 1 word, 2 bytes of data will be loaded, moved. So coming to the next one, far. Far refers to the memory location outside the current segment. Like we are using one data segment here and another data segment in another location. Data ends. So here if I was mentioning far, this call function will mentioning that far. So whatever the subprogram you are calling, that subprogram belongs to the other segment, another segment in that procedure. So if our call and return functions are mentioning in other segment, then we need to use far assembler directive. When the subprogram which we want to execute in this particular main program is within the same segment, then you can use near assembler directive. So these are the difference between the far and near. Within the same segment, then you can use near. Within the other segment, if the subprogram which we need to execute belongs to the other segment, then we will call it as far. So coming to the linking directives, there are two linking directives, which is public and external. So we are assigning one value to the variable. So here I was declaring var1 variable as public. So if I was declaring one variable in this particular segment as public, this variable can be used in the other segment or other subprograms also by writing extern in that program. So if I here public var1, here I was declaring that var1 variable 1 as public. So though we are initializing this variable 1 in this particular segment, we can use this particular variable in another one also by using extern. Extern represents that this variable is declared in the external module. So coming to the next one, equate directive. So basically in microprocessor programming, we will use count in this particular CX register, like count. CX register is usually used to hold the count value. So if I want to declare the one variable with that particular value throughout the program, so I can use this assigning of equating the constant values to a particular label. So here I was equating whenever I use pi throughout the program, that represents a value 3.14. So I want to declare a constant value for this particular variable with the label name. So here P1 is the label name. I was using equate. Equate means 3.14 value will be assigned to pi. So whenever I was using pi in the whole program, so at that particular instance of time, the pi value is 3.14. Defining constant as by using label where. So it will execute readability. The purpose of using equate is it will maintainability, easy maintainable, easily understandable and easily conveyed. So coming to the practical examples, which this is the one example here, origin. So the highlighted part is the directives which we have discussed in this particular slides. So here origin, the address location will start with the 40. So the memory which we are using will start with address location 40. Next, data segment. In data segments, I've been using even. So only even locations will store the data. Now coming to number 1, I was allocating 1 byte of memory to store 10 and another byte of memory to store 20. So the address, the location where 10 will store is 4 zeros because it is an even memory location, and then the odd memory location, no, because I have mentioned here even, only even address locations will get fetched, and in 0002 this 20 data will be stored. Next, I want to allocate some empty locations also. Next, 0004 location, 6 location will get like 5 duplicate memory locations will create, and this particular memory locations, the data is 0 duplicate memory locations. 5 duplicate memory locations will be allocated. These are the data segment. Now I am using the code segment. By using code segment, so I was linking I was linking the segment to that particular segment register. So in this particular program, I'm using only two segments, CS and DS. You can use, if you want, if we are performing operations on strings, you can use ES extra segment. So if you are particularly using stack segment, yes, you can use stack segment by writing here assume. This links the segment. These two are used to these two are the instructions used to initialize the data segment within the code segment. Now number 1, here what the value number 1 label, we have already mentioned the number 1 label address memory location will hold the data 10. So in this particular instruction, AL is having 10H. In this so AL number 2 addition, performing addition between AL. So 1020 will get added and the output 30. So you can store this 30 in APR by using here another instruction, move ARR comma 30H, or you can use move ARR comma AL. So this memory location, it will go to that particular memory location. It will store, instead of 0, the output which we are getting 30 will be stored. So this is all about the assembler directives present in 8086. So until now I have discussed about the segments, what are the assembler directives present in the segments, or linking procedures, externs, all these things. So why we are using this assembler directives? Because it helps allocating memories, programming organization, program structure. So practical use to simplify the programming for better control of memory and execution flow. Thank you.